Good day. We are now on the sixth topic of quality management. And now, in this lesson, we will tackle about quality management in production that can also be called process capability. But before that, let's hear about its objectives. Objectives in this lesson: define process capability, identify the difference of CP and CPK, control limit and specification limit, determine whether and when the process is capable or not, and classify if the process is rejected and defective. So, what is quality management? Quality management is the act of overseeing various operations and duties inside a company to guarantee that the products and services given and the means employed to produce them are consistent. It assists the company in achieving and maintaining a targeted level of quality. Quality management aims to ensure that all the organization's stakeholders work together to improve the company's processes, products, services, and culture to achieve the long-term success that stems from customer satisfaction.
What do we mean by quality? A product or service is of good quality if it meets the needs and expectation of the customer, and if a product or service satisfy the customer's wants and expectations. So next is it's customer who define quality. Customers have needs and expectations like performance, appearance, availability and delivery, reliability, and of course, price. So if a product or service meets all those needs, then it means it passes the quality test. But if not, then it is a substandard. So why quality is important in business? Because customers are increasingly demanding in today's market. Customers are more knowledgeable, willing to raise concerns about low quality, and able to proportion facts approximately terrible quality, example, through emails and social networking. Quality and competitiveness. Fewer companies primarily on pricing. The higher quality product is likely to prevail at a similar price. A company's product quality might help it stand out from competitors. So, last is production. Production is a technique of mixing numerous cloth inputs and immaterial inputs like plants to make something for consumption. Also, it is an act of making an output. Quality management and production. To assure quality improvement, procurement, and production procedures, a proper product uses production strategies to reach the desired quality, whether they deliver raw materials, components, or complex assemblies. Suppliers must be monitored to be verified that they adhere the supplier's agreements. Also, production preparation and support as an integrated element of production manufacturing are examples of process optimization in the manufacturing process. So the can be done or evaluated using KPIs and figures like CPK values. So quality management in production has three major features. First is inspection plan management. Inspection plan management is an essential aspect of quality control. In the early phases of the project's life cycle, efficient quality and inspection planning are required due to the complexity of the process. The inspection standard for the company's whole quality-related operations and the control strategies for ensuring product and are quality processes and quality are defined here. So second, supplier quality management. Supplier can be an essential rule in development of new product for any organization. Like companies increasingly enlist suppliers to deliver specific parts and components as they explore methods to improve quality and cut costs. And also, suppliers evaluate process aids in the clarification of rules and the setting of acceptable expectation. However, in this process, you must ensure that each of your suppliers meets your expectations and a good fit to become a business partner. Lastly, is quality inspection and statistical process control or SPC. It's a methodology for measuring and controlling quality across the life cycle. It contains tools to aid in the detection of tolerance variation, the identification of root causes, and the correction of faults. Users control, generate a control charts in a typical SPC process to graphically visualize and differentiate between coincidental and systematic quality that, that influence the production.
So let's move on to specification limit versus control limit. So when we say control limit, it is the limit of variation that is expected from a process and is said to be statistical control. So when we say statistical control, it means that the only common cause of variation exists and no special cause of variation present. Such processes show consistency in their performance over a period of time. It is also calculated from a process itself and shows how the process is performing and also refers to as the voice of the process. There are also two types of control limit, the upper and the lower, which is also known as UCL and LCL. Both could be calculated using mean and standard deviation. UCL is mean plus 3 times standard deviation, while LCL is mean minus 3 times standard deviation. In some instances, the lower control limit might come to a negative value, but we'll just take it as 0 since there is no point in going behind 0. In short, control limit is based on the performance of your process. These values are calculated from data and they tell you about the variability in your process, while specification limit basically set by customers and referred to as the voice of the customers because they represent the value which the customer requires. They're also the limit on the product characteristics that define where the product work and where it will not work. And if the product falls outside, they expect the item will be rejected. So in general, there are two types of specification limit, the upper specification limit and lower specification limit, or USL and LSL. And this specification limit should be placed at a point where the losses due to variation equals the benefit of the product. And these limits also are often but not always symmetric if your part falls within upper specification and lower specification. So part will be meeting your customer expectation, but if it falls outside this range, it will be rejected. It is also used to determine the process capability and the sigma value. So in summary, the control limit talks about the process while the specification limit is all about the customer's requirements. So now let's talk or let's I'll give you an example on what is the difference between control limit and specification limit. So Control limit has no relation to specification limit. And let us understand this with the help of an example, which is a car parking. So let's say you are trying to park your car in your garage, and there are three possible and necessary scenarios. First case, when control limit falls within the specification limit, think in this case the cost of your garage as your specification limit, which is defined by customer. If your control limit falls within your specification limit, if you park your car in the middle, it will always have a room on both sides. That is one of the reasons the Six Sigma philosophy of focus on removing variation in the process. Next, let's take another case. In this case, when the specification limit coincides with your upper control limit, the car will only a little bit smaller than the garage, but you can still fit the car in the middle of the garage or center of the specification. If you want to fit your car inside, this will be the least probable case because you're almost on the edge of specification limit. Third, third case, so when the specification limit falls between the control limit, that means your car is too wide for a garage and nothing you can do the strength of the process that can help you. In this case, you need to change the dispersion of the process. That means you have to make the car smaller. So when control limit exceeds the specification limit, therefore, some part of the process will be functioning outside the specification range. And when the range of control limit is greater than the range of specification, the process will start producing defects.
So, specification limits are the values between which products or services should operate. These limits are usually set by customer requirements, like for example, you print labels for shipping process. If the labels are too big or too small, they will not fit into printers properly. It's natural for a manufacturing group to be concerned with the product's specification limits, the upper and the lower limits imposed on the process. Specification limits are sometimes designated by the producer definition of quality or most frequently a customer in an attempt to narrow the distribution of a product's properties. Unfortunately, to keep a process in control, teams often develop strategies based on those specification limits instead of ones that better reflect the natural variation of that process. How are specification limits different from control limits? So, control limits are calculated from process data. They represent how your process actually performs. Specification limits are defined by your customer and represent the desired performance of your process. Specification limit and control limits are used for different purposes. Control limits let you assess whether your process is stable. Specification limits allow you to assess how capable your process is of meeting customer requirements.
Next is control limit, determined based on the procedure, demonstrate how the process is expected to perform, such as through system variation or the variety of products that the process generates. Next is typically control limits are set at less 3 standard deviation from the mean. Two control charts are used to evaluate the characteristic of variable data. One to indicate the stability of the process mean and another to characterize the stability of variation of individual data values. Next.
So, example of control limit. So this is our first example, which is the P chart. So here's the example of the table. First, we will add all the non-conformers, which is the total is 119. Next, we will add all the sample size, which is the total is 2,249. Next, we will apply the formula, which is the P bar equals total number of defective, which is the or non-conformers, divided by total of number of sample size. So, P bar equals 119 divided by 2,249. So, P bar equals, the answer is 0.053. So, next, we will apply the formula of the proportional of non-defective items. So, the formula is Q bar equals 1 minus P bar. So, equals 1 minus 0.053. So, the answer is Q bar equals 0.947. So, next, we will solve the average. So, the formula of the average is N bar equals total number of sample size, which is the 2,249. So, divided by number of sample. Number of the sample, which is 10. So, 2,249 divided by 10. So, the answer is 224.9. So, control chart for P. We will now solve the upper control limit and the lower control limit. So, the upper control limit, which is the UCL equals P bar plus 3 square root of P bar times Q bar divided by N bar equals 0.053 plus 3 square root of 0.053 times 0.947 divided by 224.9, which is the answer is 0.098. So next, we will solve the lower control limit, which is the LCL. LCL equals P bar minus 3 square root of P bar times Q bar divided by N bar. So, our P bar is 0.053 minus 3. So, our P bar again is square root of 0.053 times the Q bar, which is 0.947 divided by the average, which is the N bar, which is 224.9. So, the answer of our lower control limit is 0.008. So, this is our P chart, our chart. So, now, we have the control limit. So, we can go ahead to the proportion. So, we can see here that the proportional defective is higher than the upper limit. We recommend checking for the case, usually higher value and under survey. So therefore, the process is out of control. So this is our P chart. So the next example is the C chart. So this is the table of our example of C chart. So first, we will add all the non-conformers, which is the total is 86. So next is we will find the center line. So which is 86 divided by 10. Ang kanang 10 kay mao na ang total of shape. 10 man kabo katong shape, so 86 divide 10. Ang 86 diha na sa total of non-conformers, which is equals 8.6. 8.6 is the answer. So next, we will solve the upper control limit and the lower control limit of the C-chart. So first, we will solve first the UCLA, which is upper control limit. The formula of upper control limit of P chart is C bar plus 3 square root of C bar. So, UCL equals 8.6, which is the answer of our center line, the C bar, plus 3 square root of 8.6. So, the answer is 17.4. So, the lower control limit LCL equals C bar minus 3 square root of C bar. So, 8.6 minus 3 square root of 8.6, which is the answer is 0.2. Since we don't respect the negative of non-conformers, we normally replace the negative to 0. So, kanang negative 0.2 diha 0 na siya ang answer ana sa lower control limit niya. So, this is the chart of the C chart. We can see here that we have a positive strain. The number of non-conformers is increasing on average over time. They suggest that the process performance is degrading over time. Therefore, the process is out of control. Some corrective measures need to be taken. So this is the chart of C chart. Thank you.
Species control charts. All control charts have three common elements, which is the plot points, center line, and control limit. Plot points usually represent individual measurements, averages, standard deviation, or ranges. And the center line is usually but not always the average of the point plotted on the chart. And the control limits represent the amount of variability in the process.
So, what is process capability? Process capability is defined as a statistical measure of the inherent process variability of given characteristics. This can also be used to assess the ability of a process to fulfill the specifications. A capability analysis is an excellent tool to demonstrate the extent of an improvement made to a process. It can summarize an excellent deal of data simply showing of an improvement made to a process. It can summarize an excellent deal of data simply showing the capability of a process, the amount of improvement needed, and later the amount of development achieved. Next. So why do we measure process capability? In manufacturing and different kinds of business, decreasing waste and providing top quality product is vital to living on and thriving in the present day marketplace. Waste exists in lots of forms in an existing process. When we look at the bigger picture, process capability is more than simply measuring the CP and CPK values. The process capability is only simply one tool within the statistical process control or SPC toolbox. Implementing SPC includes collecting and analyzing data to apprehend the overall statistical performance of the technique and become aware of the reasons of variance within. The vital knowledge is acquired through specializing in the capability of the process. Monitoring process capability allows the manufacturing process's overall performance to be evaluated and adjusted as required to guarantee that the product meets the design or customer's requirements. When used effectively, this information will lessen scrap, improve the product quality and consistency, and also decrease the cost of manufacture and reduce the cost of bad quality.
When to use process capability. Use the standard method for calculating process capability analysis when you answer yes to all the following questions below. Is it necessary to know how the system performs as compared to specification limits?
Specifications or requirements should be obtainable to complete capability analysis. The system must also measure the same way as the specifications. Thus, a direct comparison can be made.
Does the specification contain a higher and lower requirement?
For processes with one-sided specifications, see the article Capability Analysis for one-sided specifications.
Are no special causes of variation present?
A system with special causes is risky and continuously changing. If capability analysis is done under those circumstances, it is going to be unreliable. Always construct a control chart and check for special causes before finishing capability analysis.
Is the data in variables form?
In order to finish the quality method for capability analysis, the data should be in variable form. That is, measured data such as time, length, weight, or distance.
Do the individual values form a normal distribution?
In order to complete capability analysis using the standard technique, a normal distribution is required. Use a histogram to test for normal distribution. If the distribution is not standard, a non-normal capability analysis may be used.
Has the data been collected over a period of time?
There are two ways to gather data for capability analysis. The standard method is from a control chart, where the data is collected over some time. If data has been collected during this way, the standard method for play-acting capability analysis is used.
Capability analysis is for one-sided specifications, trial runs, characteristic data, and non-normal data are all included in the practical tools for continuous improvement.
First example, food served at a restaurant should be between 39 degrees Celsius and 49 degrees Celsius when it is delivered to the customer. The process used to keep the food at the correct temperature has a process standard deviation of 2 degrees Celsius, and the mean value for this temperature is 40. What is the process capability of the process? So first, let's write the given. Upper specification limit, or USL, equals 49 degrees Celsius. Lower specification limit, or LSL, equals 39 degrees Celsius. And our standard deviation equals to 2 degrees Celsius. Our mean is equals 40. So what is asked? So we need to find the process capability. The formula of process capability, or CP, equals to upper specification limit, or USL, minus lower specification limit, LSL, over 6 standard deviation. So now let's solve for process capability. CP equals to USL minus LSL over 6 standard deviation. So our value of USL equals 49 minus 39 for LSL over 6 times 2 for our standard deviation. So 49 minus 39 equals 10 over 6 times 2 equals 12. So our CP is 0.833. So this is now our answer. CP equals 0.833.
The XYZ Private Limited Organization is manufacturing oil sump in their quality assurance plan. They have mentioned the pouring temperature or process parameter of the melting process is a critical characteristic, so they have decided to monitor the CP. In their collected data, they have an upper specification limit of 1,410 degrees Celsius and lower specification limit of 1,319 degrees Celsius and a standard deviation of 0.623. To find the process capability, let's proceed now by using the CP formula, which is upper specification limit minus lower specification limit over 6 sigma, or other called standard deviation. Based on the given data, we can now input the USL and LSL. So, 1,410 minus 1,390 over 6 multiplied by the standard deviation of 0.623. 1,410 minus 1,390 is equal to 20, and 6 multiplied by 0.623 is equal to 3.738. 20 over 3.738 is equivalent to 5.351. In sample problem number 3, we have pizza box should be between 38 millimeters and 49 millimeter in order to keep the food warm for a longer time. The box can absorb the mean temperature of 20 and a standard deviation of 2 during the delivery. Compute the CP. The given data are USL is equal to 49 millimeters, LSL is equal to 38 millimeters, mean is equal to 20, and standard deviation is equal to 2. The formula for CP is equal to USL minus LSL over 6 multiplied by standard deviation. So we can put 49 minus 38 over 6 multiplied by 2. 49 minus 38 is equal to 11, and 6 multiplied by 2 is 12. 11 over 12 is equivalent to 0.92.
Standard deviation is a measure of variability in a process. It's a statistic that determines how far a data collection deviates from the mean. And by determining each point's divergence from the mean, the standard deviation is calculated as the square root of the variance. So the standard deviation increases as the data set becomes more spread out. For example, when applied to an investment's annual ROR, the standard deviation reveals the investment's historical volatility, which is the rate of the increases or decreases of the price tag over a particular period of time. So the larger the standard deviation of security, the more significant the difference between each price and the mean, indicating a more comprehensive price range. So the formula for standard deviation is square root of the squared x minus mean over n. And many statistical methods utilizes the standard deviation to estimate variability. It means a summary of statistics that represent the amount of dispersion in a data set. The key point is that the standard deviation is an object measured of variation. Focusing on minimizing the standard deviation of key process characteristic will result in higher quality and customer satisfaction.
So moving forward to another topic, which is the Minimum Process Capability Index, or known as CPK. The K in CPK stands for centralizing factor. It measures actual capability and it provides comparison between output of process versus process specification. If CPK indicates whether the distribution will potentially match within the specification, CPK indicates whether the overall average is located in the center. The CP and CPK values will be the same if the total average is within the specification center. CPK can never exceed CP, so CP can be seen as the potential CPK if the overall average is centrally set. The formula for CPK is equal to the minimum of CPU and CPL, where CPU is equal to USL, or the upper specification limit, minus X bar, or the mean, all over 3 times standard deviation, and CPL is equal to X bar, or the mean, minus LSL, or the lower specification limit all over 3 times standard deviation. So interpreting the process capability index. When CPK is negative or less than 1, it indicates that the mean of the process is shifted from target and defects will be produced. The process will produce output that is outside the customer's specification limit. When CPK is greater than 1 but less than 1.67, the process is said to be fair. And lastly, if the CPK is 1.6 is greater than 1.67, the center or mean of the process may be shifted from target but still the process is capable of meeting design specification. The larger the CPK, the better. The less likely it is that any item will be outside the specification limit. We generally want a CPK of at least 1.33 that has 4 sigma or higher to satisfy most customers.
So, here are some capability index or CPK example. First, the quality assurance manager is assessing the capability of a process that puts pressurized grease in an aerosol can. The design specification called for an average of 60 psi of pressure in each can with an upper specification limit of 65 psi and a lower specification limit of 55 psi. A sample is taken from the production and it is found that the cans average are 61 psi with a standard deviation of 2 psi. What is a CPK? So we are asked to find the CPK. So first we have to interpret the data and after, so here it is. Upper specification limit or the USL is equals to 65. Lower specification limit or the LSL is equals to 55. Standard deviation is equals to 2. Mean is equals to 61. So, CPK equals minimum of X bar or the mean minus LSL over 3 times standard deviation or USL minus X bar over 3 times standard deviation. So first, we have to find the process capability based on the lower specification limit. So, X bar minus LSL over 3 times standard deviation. So substitute 61 minus 55 over 3 times 2 is equals to 1. So next is the CPU or the process capability based on the upper specification limit. So substitute 65 minus 61 over 3 times 2 is equals to 0.667. So as you can see, we have different values from the lower specification limit and the upper specification limit. So CPK equals minimum of 1 or 0.667. So our CPK is equals to 0.667. So as you can see, 0.667 is lesser than 1. So the process is not capable.
Example number 2. Find the minimum value if the net weight specification is 9 ounce plus minus 0.50 ounce, process mean is 8.80 ounce, and the process standard deviation is 0.12 ounce. First, identify all the given. Our USL or upper specification limit is 9.50. Our LSL or lower specification limit is 8.50. Our standard deviation is 0.12 and the mean is 8.80. So what is asked is the minimum value of CPK, and for the solution, the formula of CPK is equal to the minimum of mean minus LSL all over 3 times standard deviation and USL minus mean all over 3 times standard deviation. Now substitute all the given values. Our mean is 8.80 and our LSL is 8.50 all over 3 times standard deviation, which is 0.12, and that gives us an answer of 0.833. Our USL is 9.50 and our mean is 8.80 all over 3 times 0.12, and that gives us an answer of 1.94. Now, the minimum value is 0.833. Since our CPK value, which is 0.833, is less than 1, the process is not capable.